Hello everyone. In the last lecture, we saw about the alkylation, limitations of alkylation, that is Friedel-Crafts alkylation, and I had given some exercises and we discussed about it. And I had missed a point as well. So I had explained how the carbocation is formed in RX, which I had missed in the previous class. So now coming to the current, and I had told that I would be explaining, so I think I'll take up this part in why these are deactivating and these are high and this is highly activating, and I'll give further examples of highly activated groups as well in the next class, I guess, or class after that. Okay, so now let's talk about Friedel-Crafts acylation. Okay, Friedel-Crafts acylation. What is an acyl? Acyl group is something like this. Acyl group as this. Okay, this is an acyl group. So basically what happens is this groups is getting attached on the benzene ring or an aromatic ring, and as it is a Friedel-Crafts reaction, we use the same Lewis acids. Lewis acids are used. Okay, and this is an acyl group, and I have shown you some examples of this acyl group as well. These are benzyl group and this is acetyl group. We are gonna take Lewis acid and then as the acyl group, acyl cation. What is an acyl cation? Coming to talk about acyl cation is this. This is very stable. The acyl cation is very stable and they do not undergo rearrangements. They generally do not undergo rearrangements. Why? Because of the stability. As the acyl cations are very stable, so these do not undergo rearrangements. So they do not undergo rearrangements. You can just assume, and it is because of the donating effect. There are lone pairs over here, so this donating effect can be seen. So due to which the acyl cations are very stable and no chance of so there's no chance of rearrangement. Generally, I'll give you a point where you might see, you will see rearrangement happening, and as acyl benzenes do not, okay, that's all, they don't disproportionate or rearrange. That's what is the point. And we had talked about polysubstitution in Friedel-Crafts alkylation. Is polysubstitution possible in this case? The answer is no. The product formed after the acylation is very stable, that is least reactive, I mean less reactive. So the further acylation is not supported or is not possible due to its stability, and due to stability it is least reactive, so polysubstitution is not possible. Okay, I'll give a point, just write down polysubstitution is not possible. Okay, and now talking about the reagents, what are the reagents taken in this reaction? We take this what is this? Acid halide, carboxylic acid halide basically, and Lewis acid as well. Lewis acid. Okay, let in our case AlCl3, or it might be FeCl3 as well. Generally AlCl3 is taken as it is easily available, and it has better yield as well. And if you don't take acid halide, even one of these things, other type of reagents that can be used. Okay, one more thing is PCl5. This is also, I think I had forgotten. Okay, this is also possible. So similar characteristic that is seen between alkylation and acylation is that when they have highly activating or highly deactivating group present on the on the aromatic ring, so Friedel-Crafts acylation and alkylation both are not possible. This is the like feature that is seen among both of them. Okay, so now let me talk how the reaction happens. So the common tendency that AlCl3 will be accepting the X, I mean the Lewis acid will be accepting the halide ion, and you will be left out with this acyl cation, and that acyl cation will be attacking one of the positions on the benzene ring. Okay, we get something like this. This is the major product font. I think that's all about Friedel-Crafts acylation. Okay, if you want and you are curious about how the mechanism proceeds, I will be showing you the mechanism. Yeah, this is acid halide, and this, and AlCl3 accepts it, accepts the Cl minus, and we see this type of acylinium ion, which is a resonance hybrid. You get to see this. So due to which I told you the stability, and the reason for the stability is this resonance, and you can see the mechanism as well. So this bond goes and attacks, and then this H will be accepted by the Cl. So at last the H, this H and Cl, we get HCl, and further the reaction happens. Let's say similar kind of reaction happens. Then what happens is when you hydrolyze it, we get this type of product as an intermediate, and we take water and we hydrolyze it. It is liberating a ketone and hydrolyzes the Lewis acid. We get HCl as well. So now going further, I had talked about the activating rings, activating groups and deactivating groups as well, that we'll be discussing it. So I think we should go for the discussion of it now, as we have completed almost all the reactions. We'll be seeing that under the section effects of substituents on the reactivity. Okay. We'll be studying it. Look at the mechanism and this mechanism. I think this mechanism is clear to all of you. So now we'll study about the disubstituted benzene and then reactivity in presence of the groups, and we'll be doing some questions on them, and what happens in polysubstituted rings. That is the choice of point of attack. Till now we just dealt with the benzene rings, so due to which due to its symmetry, we had not considered anything regarding to the point of attack. So now it's time for that, and we'll be seeing some miscellaneous reactions that are okay. Let me go through this. Okay, clear. As we are clear with this, so effects of substituents on reactivity. Let's say we have a group attached to the ring G. If this belongs to plus M plus I plus H groups, so this will be an activating group, and if it is a deactivating group, if G is an electron releasing group, let's say if G is electron withdrawing groups, EWG groups, that is minus M, minus I, minus H. I think these notations must be clear. That is M denotes mesomeric effect, I denotes inductive effect, H denotes hyperconjugation. So which we had seen in general organic chemistry, the inductive effect and mesomeric effect, that is the resonance effect, and hyperconjugation. It is also known as backbone resonance, right? Sorry, no bond resonance, not backbone resonance, no bond resonance. So when a group is any of these three, the substitution, okay, I'll be giving notation to it. This is ortho position, this is meta position with respect to this G, and this is a para position. And again, due to symmetry, this is meta, this is ortho. If the groups are plus m plus I groups, we get, and we'll have substitution at O or para, ortho or para. If we have the negative groups, I mean minus m or minus I or minus h groups, we have substitution at meta position. Okay, let me give you some of the Friedel-Crafts okay. Let me give you the list of the donating groups. I'll talk with respect to activating. Okay, this is activating, this is deactivating. I mean these. I'm sorry. Okay, deactivating groups. Let me give among the activating groups we have very strong deactivating, a strong activation, and this is provided by the groups. Like if groups are O minus, okay, I'll be giving in the increasing order: NH2, NHR, these are the lone pairs, and this ENR2. R can be any groups, any group, any carbon group attached to it. Okay, and now strong activation. Strong activation is seen in groups like OH or coming to the moderately activating ones. So this helps you determine the point at which the incoming electrophile attacks. Now talking about the weakly activating groups. I can tell. Okay, for that activating, let's say. If G belongs, if G is CH3, okay, this is activating, and the weakly activating are X groups, that is halide groups. And okay, one might question that halide shows minus I as well, plus M, but why don't we consider minus M and consider it as a deactivating group? Let me give a note on it. Due to lone pair delocalization, due to lone pair delocalization, delocalization. This turns out to be ortho or paradirecting. We had seen in the general organic chemistry that we considered minus I over plus M. Am I right or wrong? Yeah, we had considered for halide groups that minus I to be stronger over plus M, but due to lone pair delocalization, these act as the orthoparadirecting. So that's why we consider it specially as weakly activating groups. And now coming to the deactivating groups. Deactivating groups, we have this G. If G is CCl3, it is deactivating. Why CCl3? This shows minus H and minus IFH. Okay, in this case, we get to see that it is meta-directing. Okay. Okay, let me mention in this places that meta-directing. And here that it is orthoparadirecting. So due to which you will be able to decide, it will direct the electrophile towards that particular position with respect to the group pre-attached to it. And now strongly deactivating. This is just deactivating group, and now the stronger deactivation is seen in. We don't have many groups in this. Strong deactivation in is seen in this. Okay, this is G again. If G is NO2 or a cyanide group or aldehyde group. So this will be these are very strong meta directing. So whatever the product will be formed at meta. I mean, the electrophile will be directed towards meta. Okay. In the next lecture, we'll be seeing some questions on the directions, some brain tweaking questions as well, and okay, wait. Before that, let me give you some 2 or 3 cases. What if there is a disubstituted ring, in the sense 2 groups are already attached. In that case, if there are two groups, for giving questions, let us do this. Let's say our case 1 is this. It says that 2 groups, X and Y, attached. Okay, it can be anywhere. This Y can be even here at this position. This Y can be at this position as well, this position as well, this position as well, this position as well. So we are just considering the general case. and let's say what will happen. I'll be giving 3 points, and with that you'll be able to judge how it is going to happen. If x and y both are activating, then E plus will be attached at ortho or para with respect to the stronger activator. Among this, whichever is stronger, with respect to that, you will be attaching the electrophile will attack the ortho position with respect to the stronger activator. If now case 2, if one is activator and y is deactivating. We see that E plus will be attached at ortho or para with respect to the one which is activating group with respect to x, and if both are deactivating, then we'll consider meta position with respect to strong deactivator. Okay, so that's all for today. We'll be talking about we'll be doing some questions, and we'll be talking about some extra reactions that we are going to learn, and some of the exceptions that we are going to see in the next lecture. Thank you.